It's always fun to start talking about science with the Greek philosopher Aristotle. It seems certain that there were other humans in the past that had very interesting ideas, but for one reason or another, we end up with Aristotle's works. You see, Aristotle is a great place to start our discussion of science, because Aristotle wasn't a scientist. I know, that seems crazy, but it's true. Although I never got a chance to hang out with Aristotle, I mean, he lived over 2,000 years ago. I can still pretend what he would do. We can then look at how he thought about stuff compared to other humans that are scientists. Take a box that's sitting on the floor and then push it. What happens and why? For Aristotle, he starts with the following assumptions. If you push a box, it moves. If you push harder, it moves faster. If you stop pushing the box, it stops. Once he had these starting assumptions, he could produce the following conclusion. The natural state of an object is to be at rest. If you leave it alone, it will stop. That seems as logical as heck, because heck is super logical. It makes so much sense that if you go out and ask some people about pushing blocks, they would likely agree with Aristotle. Aristotle was wrong. In fact, the natural state of an object is constant velocity. That means if you get it moving and then leave it alone, it will keep moving with a constant velocity. Oh, I know what you and Aristotle are thinking. But that wouldn't happen with a box on the ground. I agree with you. But here's the problem. A box on the ground isn't left alone. There's also a frictional force between the box and the floor. If you remove the floor and the air and put the box in outer space, it would just keep moving forever. What went wrong? The problem was that Aristotle used deductive reasoning. He started from assumed truths that everyone could agree on. Then he could deduce all the details. My all-time favorite example of deductive reasoning is the scene from Monty Python and the Holy Grail, in which Sir Bedivere tries to reason an angry mob to determine if a woman is a witch. Essentially, Bedivere leads them through the following thought process.
Why do witches burn? A wood sink in water.
No, it floats. It floats.
What also floats in water, and therefore...
A witch! A witch!
That's fun, right? But the point is that deductive reasoning starts with some ideas, and then works out all the details. In the example above, everyone assumed that wood floats, which is not always true. The other logical strategy is called inductive reasoning. Instead of starting with big ideas, it starts with the small things. We call these experiments. Once you have enough experimental evidence, you can use that to build up to a larger idea. Consider this. With deductive reasoning, if your starting idea is wrong, then everything falls apart. With inductive logic, your big ideas are based on many smaller ideas. One of the first humans, at least one of the first well-known humans, to use the process of science was Galileo Galilei, 1556–1642. Yes, he came more than 1,000 years after Aristotle. Instead of assuming an object comes to rest without an external push, he decided to test that with an experiment. His experiment consisted of a ball and an inclined ramp. The nice thing about a ramp is that at low angles, the speeds are small and manageable. He was able to use basic time measurements to determine the speed. No, Galileo didn't have a smartphone with a high-speed video camera. What he found was that at a very slight angle, the rolling ball would move at a constant velocity after it was pushed. From this, he assumed that in a perfect ramp, a horizontal surface would also have a ball moving at a constant velocity, without anything pushing it. Boom, Aristotle was wrong. You see, Galileo didn't start with some big assumption. He had an experiment to create many small ideas that pointed to one larger one. That's inductive reasoning, and that's the way we do science. Don't worry. I'm going to go over forces and motion in a later chapter, but for now I just wanted to use this as an example of what isn't science. So, what is science all about? Here is my best and shortest description of science. Science is the process of building models based on real-world evidence. See, that's short and simple, right? But that leads to the next question. What is a model? There are lots of different kinds of models. Physical model, like a globe. An equation, like F net equals ma. A conceptual model, domain model of magnetism. Computational model. Yes, a computer simulation can be a model. Let me give you my favorite scientific model example, since it shows some important aspects of the nature of science. Check this out. Its moon globe from around 1950 or so. Can you see why this is so awesome? Half of the moon globe is just freaking blank. Do you know why? Well, if you don't look at the moon very often, you might not notice that you always see the same features. That's because the moon is tidal locked to the Earth. The moon both orbits the Earth and rotates on its own axis at the same rotation rate, mostly. This means the one side of the moon faces the Earth, and the other side faces away all the time. So, how do you build a model, an actual physical model in this case, of the moon? Well, you would need to go on the other side of the moon and take a look at it. However, in 1950 they didn't have a spacecraft to get over there and take pictures. That didn't happen until 1959 even then. I'm not sure anyone could get those photos as they were probably classified. But that leaves us with a moon model that's blank on the backside. What does this tell us about science and models? It says that in science we build models based on the evidence we collect. We know that we don't know everything, and that's okay. It's fine to build a partial model, and then update it later even if later becomes never. Okay, let's get this out of the way. There's some science phrases that get used quite a bit, but they don't really match up with the nature of science. Let's get started. Oh, just to be clear, I think we should just stop using these words in science. However, looking at how these things are wrong can help us understand science. Hypothesis. If you ask pretty much any middle school kid, they will automatically tell you that a hypothesis is an educated guess. But what the heck does that mean? I think someone decided to make a two-word summary of the idea of hypothesis, and it didn't turn out too well. However, it did turn into a catchphrase that students can memorize, so that's nice. Then what does it really mean? Let's recall that science is the process of building models. With that in mind, a hypothesis is the predicted outcome of an experiment based on that model. Let me give a quick example. Suppose I have this model of force and motion that says the net force on an object is equal to the product of its mass and acceleration, F net equals ma. According to this model, if I double the net force on an object, but keep the mass the same, the acceleration will increase by a factor of 2. That's my hypothesis. I can then test this with an actual experiment with actual forces. It's not a guess. Theory. Here's another one that gets used quite often. In this case, I think there is a legitimate non-science version. So let's just talk about this word as it is used in science. The very common use of the science version goes something like this. A theory is just a personal belief. You think climate change is caused by humans producing carbon dioxide, but my theory is that it's because of the sun. It's just a theory. Okay, but what does it really mean? It's basically just a scientific model. Oh, sure, you could go into the technical details about the difference between a theory and a model, but model is a much better word. It shows that we build something to represent a phenomena. That's how science works. We never build the truth, just models. Scientific law. Another tough one. A common idea about scientific laws is that these are theories that have been sent to the Scientific Congress and signed by the president of science to become a scientific law. Nope. That's not how it works. Another view is that a scientific law is something that has been proven to be true. Nope. First, you can't prove things to be true in science. My favorite example is that of a dropped ball. You would probably bet a large sum of money that if I hold out a ball and let go, it will fall. I mean, we've seen that happen countless times, but that doesn't prove it always happens. To do that, you would have to drop it all possible times until the end of the universe. So, we can't really prove stuff to be true. I actually already said that above. Second, what the heck is a law? In science, a law is a generalized principle that can be applied in many different situations. One of the famous ones is the law of conservation of energy. This says that if you have a closed system, no energy input or output, then the total energy of that system must be constant. But it's not a specific model, so we call it a law. I mean, it's still a model, so we don't actually need this word. The scientific method. I put that one in all caps because it's clearly the most important thing ever in science. I mean, why else would it be displayed in just about every single middle school and even high school science classrooms? It says that humans do science something like this. Start with a problem. Why would you do something scientific if not to solve a problem, right? Wrong. Example. Which brand of battery lasts the longest? Research. You can't do any science without first looking at what has already been done on this topic. How else could you stand on the shoulders of giants? Create a hypothesis. In science fairs, This is basically an educated guess. Example: I think that the Duracell batteries will last the longest. Perform the experiment. How can you have a science project without data? Example: connect different batteries to light bulbs and see which one lasts the longest. Analyze the data. You have to do something to the data. If it is just raw data, it isn't science. Example: average the times for different batteries to keep the bulbs glowing. Oh, if you need to, you can go back to your research and start the process over. This is sort of like using your last bird in Angry Birds, but you didn't knock over all the pigs. You start over. Create a conclusion. I recommend always starting your conclusion with my hypothesis was correct. Example: the average time for Duracell batteries was the longest. They are the best. That's the recipe for doing science always. Oh, that's the way we do science, except for all of the times when they don't go this way. Here are some examples, counter-examples. In 1928, Alexander Fleming accidentally left a cover off a Petri dish used to cultivate bacteria. The plate was contaminated by a mold that contained penicillin. In this case, there was no problem or question to start with. It was an accident. Albert Michelson and Edward Morley built an experiment to measure the motion of the Earth through the ether, the material that people believed light traveled through. The idea was to measure the speed of light as the Earth moved in different directions. Alas, they found that the speed of light was the same in all directions. If they wrote this up as a science project, they would end with "our hypothesis was wrong." Of course, their experiment led to the development of special relativity. Beta decay is a type of radioactive process where a nucleus produces either an electron or a positron. The problem was that these electrons could have a range of energies. This just didn't make sense. If they came from the same process, energy should be constant. This led to the discovery of the neutrino. Look at just about any astronomy experiment. Most of the cool things in astronomy are first discovered, and then a model is created. So the question comes second: how do you do a traditional experiment on star formation? I guess you could start with some hydrogen and let it go, right? Well, that might take a while. Then why is the scientific method such a common middle school mantra? There's a nice answer by William McComas in the 2002 book The Nature of Science in Science Education. Springer, with a chapter titled The Principal Elements of the Nature of Science, Dispelling the Myths. In this, McComas claims that there was a 1945 publication that listed all the things scientists often do. Later, this list was converted into a form of the recipe that you so often see, and then end up in textbooks. Once something gets into a textbook, other textbooks follow, and then you never get rid of it. You can see how far this scientific method has invaded our culture. If you visit a science fair, it's hard to find a poster or project that doesn't focus on some type of hypothesis. But let me be clear, hypothesis testing is a real thing. However, most of these science projects use it the wrong way, and I blame the scientific method. Then what should we do? We should teach science as the process of building and testing models. It doesn't need to be more complicated than that. Science can get difficult enough all on its own. Thanks for watching. See you on the next one. Oh, and don't forget to subscribe.